My name's Mark. I work for Jake at Viking, and I've been asked to talk a little bit about inkjet printing tonight. I don't know a huge amount about it, but I'm better just to share some of my knowledge with you. I think there's probably quite a few people out there know much more about it than I do. Does anyone know when inkjet printing first started? Any ideas?
Normally about 10 months after you buy the machine.
Or a year in your case. 1867. Lord Kelvin, a Scot, also invented the Kelvin bridge. Those with electronic engineers will understand what that is. First enjoyed it as a trace paper system for the telegraph. And it became known because the first continuous inkjet printing system. And there are basically two serious types. This was the first. I'm told it took quite a lot to be able to interpret correctly what was written on that. Not much went on with inkjet technology until about the 1950s. And then Siemens really put some work into doing commercial strip printers. And they introduced the first medical chart printer in 1951, and the chart recorders became pretty much where inkjet printing remained for about the next 20 years. In the late 1970s, what I call the four major players, Epson, Hewlett-Packard, Canon, really started to produce what were inkjet printers as we know them today. In fact, Canon first invented what was called a bubble jet printer. We'll go on in a minute just to show what that was. Today's global market, HP, Epson, Lexmark, which is an IBM spin-off, account for the majority of commercial inkjet printer sales. I'm going to try and keep this simple, but fundamentally inkjet printing is a computer digital image which is printed down on a substrate. In a continuous inkjet stream, what you have is an ink reservoir, you have a pump, you have a piezoelectric cell, character generator, and deflection plates. The ink's pumped through the system, electrostatically charged, you have positive and negative charged ions, and in a continuous inkjet system, the positive charge stays on the print on paper or the substrate and forms the character, and the remaining ink falls into a gutter and then comes back into the ink reservoir and continues. This is probably one of the most used production inkjet systems currently in industry. Very familiar with what we're doing, simple barcoding, date coding. You'll see quite a few of these miniaturized now, and they're set up in lines to go across complete rows of systems over many meters, producing just inkjets. It's only a small fraction of ink used in this system as it's recycled going through, and that makes it pretty cheap to run. Major advantages: is high velocity, 50 meters a second, high drop ejection frequency on the cartridges, and that allows for very, very high speed printing. So used commercially for marking, coding, products and packages. The other major type of inkjet system is drop on demand. And this is the most common used in inkjet printers you see on desks, and currently today used for electronics and printing thin film. You can see here very simply an ink reservoir, piezoelectric device, a damper, and a nozzle. And very simply, it uses pressure with a current pass through in the ink, it falls through and force the ink in the image. The inks are usually water-based, and these are either pigments or dyes, but they must have a volatile component for the expansion system to work. No special materials required, and the print end's normally pretty much cheaper to produce than the continuous inkjet system we saw earlier. Drop on demand, it uses two types. It uses a resistor in cartridge, which generates heat, which expands the ink, or a piezoelectric charge, which does exactly the same, expands the ink, And as the ink extends, okay, and the bubble extends, viscosity allows finally to contract, and the inkjet is fired out of the head onto the sheet. Drop on demand technology, okay, similar cartridge you see these in everyday use. Then you see the head here spraying out the coast across the top. Applications normally go for inkjet manufacturing will be printed electronics, circuit manufacturing, RFD components, optics, lenses, food diagnostics and quality indicators. Very recently, apart from passive electronics, I've actually seen an active component built and used in a real-world process. And this was used for automatic date coding of drugs in the pharmaceutical industry. PCB manufacturing is very simple. We're all aware of print and etch technology. Obviously, inkjet potentially has its advantages, those being low cost of entry, low cost of materials, low waste, low capital expenditure. Steve and Beef are familiar with this, legend printing. It only took a year to get the moniker he's got running. Okay, but again, also very simple. Okay, what it can do, is do very high density interconnects, much more so, and it's a lot better than screen printing, a lot more cost effective. What Steve's machine hasn't got, which he's still waiting for, is auto alignment, crossouts, and barcoding. All these are available on much more advanced systems that come through and are commonly in use in quite a lot of the electronic industry. PTF, polymer thick films. This is where really printed electronics I think takes off. I think we're all familiar with PET. Most printed electronics that they use is a modified PET film, which is a coating on it, which is microporous, which allows the ink substrate, all the ink material that you're about to process to dry. Here, you use print a semiconductor. We all understand how these work. You print a dielectric. And on modern systems today, you can multi-print. In multi-head systems, you can actually do the dielectrics layer and layer as the head moves back and across the substrate. Typical examples of printed electronics are these. This is currently what we're working on. This is carbon, silver, with two dielectrics built up. And we use DPI technology, both 1440, 720, and droplet manipulation and ink drop size to be able to build the dielectric layers. These are quite common in use, mainly in the Far East. Other methods for printed electronics that you're probably familiar with: thin film technology for display screens. They are commonly printed using inkjet printing. Also, nanoparticle silver inks. Nanoparticle silver inks self-dry. There are many methods of using inkjet printing to put down conductive materials. Some of those are sintered, some are non-sintered. Sintered varieties, such as copper and carbon, they usually put down a much thicker deposit on the substrate. They use an IR head to sinter the material or meld the material. And then the commonly run at temperatures that go around 140 to 220 degrees C. Most people using PET materials who understand that temperature can be quite difficult. It's the speed that the head passes over the top of the material, which allows it to sinter the copper without damaging the substrate underneath. Nano silvers, which we've been working on quite extensively, don't require that heat. They can be printed down on the PET, paper, card, still conductive, and are self-dry. The image is not as robust as sintered inks, but it's still viable. Roll-to-roll printed electronics. Steve was on about UK manufacturing. Probably the best UK manufacturer of roll-to-roll is Parlex. Parlex do quite a lot of people know roll-to-roll technology. They also do assembly. With modern print heads, for a commercial machine. It is possible, okay, for low-cost manufacture to be done at a very, very simple level. You can take standard commercial off-the-head printers, run your image code through print cartridges through the machine, laminate the film, and you can add, if you wish, active components to the circuit. You can do that using conductive solder pastes. Laminate it with an ordinary film laminator and produce yourself a very, very, very simple, robust, flexible circuit using nanowings. In fact, we've done some of this in Viking just as a demonstration. What are the advantages and disadvantages? Well, obviously, for people who want to do development, such as laboratories, universities, people in R&D, print electronics are a low-cost entry. Buy a printer, low-cost printer, buy your materials, buy your nanowinks, you can do a very simple circuit, you can do design work on that, so you can produce double-sided, you can produce multi-layer thin film, and you can do a lot of development work at a low entry cost. Cost of a printer, cost of the film and the inks to run it without having a large amount of technology to go with it. Downsides, the circuits are simple. Speed and time to code the circuits are going to be fairly low. It's going to be a simple circuit. Is it going to replace printed circuit boards as we know them? To a great degree, yes, I think it will. The lower cost, low end RFID tag market, which is already up the Far East, will be produced using that kind of technology as today. The ability for people to be able to take it, place it on paper, place it on cardboard, and print RFID tags is already well being established. High-end conventional boards, 3D printing, I don't know. Eventually I think you could see 3D printing, flexible ink technologies, nanowinks, produce more simple multi-layer products. Again, that would probably be a lab scale style. The market for printed electronics globally in 2010 was worth about $3.2 billion. And you can see that optoelectronics takes the largest slice and continues to take the largest slice of printed electronics market. Energy sensors and radio frequencies, pretty low. What's the global market worth? Today it's worth about 5.6 million. With a target of 12.6 billion by 2016. Far East dominates this manufacture, as you're probably aware, with people like Inkjet introducing a $23 million investment into flexible printed electronics in the light recently. That's about some total about printed electronics. How many OKs do you think, Steve?
I think about 46.
Thank you.
I haven't got a clue. It's quite a lot.
Okay, I'd just like to make a few thanks to the people who have taken the information from. And it's short but sweet, and thank you very much indeed.